Dear colleagues, distinguished guests, we begin the panel session for the defense of the thesis by Peter Murzin. The thesis is submitted for the academic degree of the candidate of sciences in physics and mathematics. The specialization is 010407, condensed matter physics. The topic of the thesis is the effect of heterovalent cation doping on the activity of titanium dioxide and molecular photoprocesses in heterogeneous systems. Along with that, I would like to announce the technical break due to some technical failure that we have. And distinguished colleagues and distinguished guests, unfortunately, our technical problems proceed. Therefore, we announce an additional break up until 12. We'll try to eliminate the problem. Thank you. Distinguished colleagues, distinguished guests, we proceed. I beg your pardon for such a delay and for these problems that emerged, but fortunately we managed to overcome them. And now I proceed. We proceed. Under the order issued by St. Petersburg State University, number 7637/1, I, Yuri Chizhov, Doctor of Sciences in Physics and Mathematics, Professor, Head of the Department of Photonics of St. Petersburg State University, have been appointed the chairperson of this dissertation board. The order also approved the candidacies of the members of our board, and let me introduce them. Alexei Tsiganenko, Doctor of Sciences in Physics and Mathematics, Professor, Head of the Second Department of General Physics of St. Petersburg State University. The following members of the board are working in remote mode. Olga Vadyankina, Doctor of Sciences in Chemistry, Professor, Head of the Department of Physical and Colloidal Chemistry of the National Research Institute, Tomsk State University, from the city of Tomsk. Also, Natalia Kamanina, Doctor of Sciences in Physics and Mathematics, Senior Researcher, Professor, Head of the Photophysics of Media with Nano-Objects Division of the Vavilov State Optical Institute, St. Petersburg. Yekaterina Kozlova, Doctor of Sciences in Chemistry, leading researcher of the Group for Alternative Energy Processes of the Berezkov Institute of Catalysis, Federal Research Center of the Siberian branch of the Russian Academy of Sciences from Novosibirsk. Mikhail Varg, Professor of the Institute of Chemistry of the Oldenburg University, named after Karl von Ossietzky, Germany. Distinguished colleagues who are working remotely, do you see us and hear us? Yes, it's okay, thank you. Yes, thank you, we do. Okay, thank you. And we also have our candidate for the degree here, Petr Murzin. And also we have the thesis supervisor of Mr. Murzin, Professor Alexei Yemelin, Doctor of Sciences in Physics and Mathematics, Professor of the Department of Photonics, Deputy Head of the Photoactive Nanocomposite Materials Laboratory of St. Petersburg State University. And I would like to introduce our honorary guest that we have today, who is working with us remotely. That's Professor Detlef Bonnemann, Head of the Photoactive Nanocomposite Materials Laboratory of St. Petersburg State University and Head of the Photocatalysis and Nanotechnology Laboratory of the Leipzig University of Hanover, of the Leibniz University of Hanover. And in order to improve our quality, the quality of our connection, distinguished colleagues, I kindly ask you to turn off your microphones, but do not forget to turn them on when I give you the floor. I would also like to inform you that the panel session of our dissertation board is being recorded and broadcast on the St. Petersburg State University website, And we have simultaneous interpretation into English and into Russian. And currently we have an email address posted on the page with the live broadcast of the board session, and all the listeners can submit their questions or voice their opinion or submit their questions to Mr. Murzin online, the questions regarding the thesis or the scientific discussion. These questions will be forwarded to me by our technical service, and I will read them out during the session. Questions must be related to the presentation and the content of the thesis, and do not forget to give your name and position if you submit the question. Questions that have nothing to do with the scientific discussion or dissertation or the assessment of the dissertation will not be voiced. Under the order on the procedure of granting academic degrees at St. Petersburg State University, approved by normative acts, the session of our dissertation board is valid, providing 2/3 of the appointed board members are present. The total number should not be fewer than 4 people. Our dissertation board consists of 6 people. Everyone is with us today, including 4 members of the board that are working remotely. So we have a multimedia connection with all the members of the board. Therefore, we have the quorum for our dissertation board session. Our session should not last more than 2 hours. And the agenda is as follows. So we're going to, we've spent 1 hour already, therefore we're going to have 1 or 1.5 hours. So first comes the chairman's presentation about the documents submitted by the candidate for the degree and their conformity with the requirements. Then comes the candidate's presentation providing an overview and findings of the research, then questions to the candidate regarding the presentation. After the presentation, candidates' replies to questions, then reports on the thesis. The board members will be taking the floor in turns to provide their reviews and questions. And then it will be followed by the chairman's report on the thesis. And then we're going to listen to the candidates' comments about the reports on the thesis and replies to the questions. I believe we will change this order, and our candidate will answer the questions at once after each report of the members of the board. I believe this will be clearer. Then we're going to have some time for the open discussion. Anyone present at the defense may state their position, or they can ask questions, and I should register you if you want to speak out. I have this registration form. After that, I will ask the questions submitted during the broadcast via our website. So these are some external questions, as I call them. Then the candidates' replies to the questions, and after that we'll hear the presentation of the candidate's thesis supervisor. After that, if we need, we may have a 5-minute discussion, which is not broadcast. During this discussion, the members of the board can discuss the conferring or non-conferring the academic degree. If we don't need that, we won't discuss that. After that, we'll have open balloting, vote counting, and we take the decision on conferring or non-conferring the academic degree to Mr. Murzin, and after that, we give the floor to our candidate for the closing speech. Distinguished colleagues, any questions or comments on the agenda? No? None? Thank you, Natalia. No, no questions, no objections. Okay. Okay, if there are no objections, let me start. And first of all, I would like to ask you to switch off your mobile phones so that we won't have an interference here. Thank you. So, let me start. So that's the chairman's presentation that starts. The thesis by Petr Murzin for the academic degree of the candidate of sciences in physics and mathematics, the specialization 010407 condensed matter physics, is titled The Effect of Heterovalent Cation Doping on the Activity of Titanium Dioxide in Molecular Photoprocesses in Heterogeneous Systems. The thesis was approved for the defense by the order of the Academic Secretary of St. Petersburg State University, issued on September the 2nd, 2020, number 7636/1. Petr Murzin has prepared his dissertation based on St. Petersburg State University, and Professor Alexei Yemelin, Doctor of Sciences in Physics and Mathematics, Professor of the Department of Photonics, Deputy Head of the Photoactive Nanocomposite Materials Laboratory of St. Petersburg State University, is the dissertation supervisor. The list of 2 published works describe the research findings. They include no papers published in peer-reviewed journals recommended by the Ministry of Education and Science, and 2 papers in publications indexed in Web of Science and in Scopus. The candidate has submitted the full set of documents to the academic secretary. The above-mentioned documents comply with item 12 of section 3 of the order, and all the documents provided by the candidate for the degree correspond with the requirements and are found in the certification file of our candidate for the degree, and the curator of the defense, member of the Department of Dissertation Board Support, has all the necessary copies. And before giving the floor to our candidate for the degree, I have a question. Distinguished colleagues, distinguished members of the board, do you have some general questions to the candidate for the degree? Is there a need to tell you about all the list of provided documents? No, thank you. I believe there's no such need. Yes, I support that. Yes, I believe we won't spend time on that. I've looked through all of these documents. They are quite in compliance with the requirements, so we won't spend time on that. Now, I would like to give the floor for the short report to our candidate for the degree. Petr, finally, you have the floor. Distinguished members of the board, hello. I'm going to deliver a short presentation on my report. Photocatalysis has been known from the start of the 20th century, but the rapid development started in 1970s due to the interest to alternative energy. And among the most developed applications of photocatalysis, we have the treatment of air and water and self-cleaning surfaces. And for all these practical applications, the photoactivity increase of the used materials is quite relevant. Titanium dioxide is the most popular material, most widely used material, and it is explained by several characteristics: low cost, non-toxic character, and so on. We can outline 3 potential opportunities to improve the photoactivity. We can increase the number of charges on the surface, and we can achieve it by increasing the specific area of the surface. Then we can generate charge in a wider spectral range. And finally, we can reduce the efficiency of recombination. And this hetero shift can be an example. And doping is one of the opportunities to implement this increase in photoactivity. Doping as an approach has been known for a long time, and in literature it's mostly represented by works aimed at a specific recipe that helps to generate a more active photocatalyst with a new dopant, and this approach brings its fruit. And here we can have an example if we use titanium dioxide doped by nitrogen, and this approach has certain limitations, and we find the works that have general regularities more relevant. And the goal of this work is to detect such general regularities in the change of photoactivity. And we use scandium, aluminium, niobium, and vanadium. And we wanted to establish the interdependencies with physical and chemical parameters of the material. In order to implement this goal, we synthesized 5 series of powder-like samples. They are represented by a rutile phase, and they have a specific area of 1 meter, 1 square meter per gram. And as for the area, it was permanent for all series, and thus we can compare them. The basic experimental methods include the testing of photoactivity, and we used the decomposition of phenol in the water phase, and here we can expect the changes of electron state in the material, and this can be reflected in the change in the Fermi level, and it can be characterized by the work function of materials, and this was done by the condenser method. Then, as some of the states can be optically active, the relevant studies can be done by optical methods. We used photoinduced coloring here. And finally, part of defect states can be described by some magnetic methods. On these slides, I'm going to show the results of the work using the scandium-doped titanium dioxide, and the results on other series are given in the text of the work. So here you see the dependence of photoactivity of the received materials from the concentration of the dopant. Here you see the presence of certain concentration in which we have the maximum activity, the optimal concentration as we call it. And if we measure the work function, it turns out that in optimal concentration we observe the minimum work function. Thus we support the idea that there is a transition of the state that leads to a change in Fermi level. So let's have a look at the optic studies. The samples have coloring in the area that correspond to different centers of titanium dioxide. So in the material, we see the participation of the defects of titanium dioxide. And the signal of coloring can be represented as a sum of 3 absorption bands. And thus we can also decompose the spectrum of titanium dioxide. And if we consider each band, we see that when we overcome the optimal concentration, there is a transition. And this corresponds with a rise in the speed of coloring. And thus the results of optical studies show that there is a transition of state in optimal concentration that corresponds to maximum photoactivity that leads to the impact on coloring centers. The results of electromagnetic resonance studies also demonstrate that there is the change of the structure of the state. And indeed, in the sphere of optimal concentration, we observe the maximum APR detected centers. So thus, the results led us to the following conclusions. First of all, there is a specific concentration that corresponds to the maximum photoactivity. This is the optimal concentration. And in this optimal concentration, the work function has a minimum level that demonstrates the shift in the level of Fermi. And this is caused by the overwhelming of shallow states of scandium titanium dioxide. And this leads to the rise in photoactivity. Similar results were received for other series of doped samples. In each case, we have a specific optimal concentration for photoactivity, and in this optimal concentration, we see the extremum of the work function. And using optic and EPR studies, we demonstrated that that we have the stabilization of inert state. And along with these regularities, we've found the peculiarities for each series of dopants. For example, niobium doped series of titanium dioxide. In this case, in optimal concentration, the work function is increased, unlike in other series. And at that, the number of centers drops. And this behavior was connected with the stabilization of recombination inert centers, niobium of niobium. And this corresponds with the results of quantum mechanical calculations. And therefore, the prevalence of such centers reduces the speed of recombination. And the general conclusions can be defined as such. There is a specific optimal concentration of dopant that corresponds with maximum photoactivity. This maximum photoactivity is explained by the prevalence of recombination inert centers, and these centers are formed by both dopant atoms and by the intrinsic compensation defects of titanium dioxide, and redistribution of these defect states leads to the change in work function, and it explains the connection with photoactivity. So the main provisions are given here on the slide, and this work was published in 2 articles, and there are other publications that are being prepared, and I also demonstrated these results on 5 international conferences. Thank you very much. Thank you, Petr. And now questions on the report, if there are any. Do we have any questions on the report? No questions right now. Okay.
Yes, there might be a question.
Профессор Ван, пожалуйста.
So, Professor Wark, please.
Okay, yes.
You have the floor.
Thank you very much for this report. I just have a quite simple question to this coloration. You mentioned that you have 3 different absorption bands identified. But what is the background of these absorption bands? What are they standing for? Can you explain that a bit more?
Yeah.
Спасибо.
Yeah. So we're talking about the coloration bands, right? Actually, these coloration bands relate to several types of T3+ centers in titania, which was demonstrated by our group and by our colleagues in experiments with time-resolved spectroscopy. The main point here is that the decomposition of signal for scandium-doped titania could be done in the same way as we can do it for pristine TiO2, which implies that we observe compensation by the same, or more or less the same type of centers in doped titania as we do for undoped. So it highlights the important role of self-compensating centers of titanium.
Спасибо. Профессор Варк.
Thank you very much, Professor. Are you satisfied with the answer? Okay, let me ask the question then. The question is as follows. So, Petr, in your studies, you used electron paramagnetic resonance. Certainly, this is quite an efficient method, and it allows to assess the behavior of an ensemble of paramagnetic particles, centers, and so on. Yet, my question is as follows. As far as I understand, you carry out these studies under the atmospheric pressure, and we know that oxygen is a paramagnetic gas, and it can be absorbed on samples, and it can introduce its own signal in this ensemble. So how did you take this effect into account? Thank you. Indeed, in this work, the studies were carried out in the air atmosphere, but it helps us that the area of oxygen absorption is not overlapping too strongly with another absorption band. And I agree that vacuum studies would be an interesting continuation of the work, because it would allow us to divide some of these peculiarities. Thank you. Thank you. I'm quite satisfied. Any other questions? Okay, thank you very much. Then let's shift to our next item in our agenda. And I am to ask whether we have any external reviews, not from the members of our dissertation board. No, none of that. Okay. Now it's time to give the floor to the members of our dissertation board. And I have just one idea. As all the reviews were already published on the website of St. Petersburg State University, I offered to read them out, or maybe to give some basic provisions, some basic points, just the remarks to the candidate for the degree, bypassing all the other issues on the structure of the dissertation and so on. Any objections to that? No? No objections? Okay. Then it's universal acceptance. And now I would like to give the floor to Professor Tsyganenko. Alexei, please, you have the floor. Distinguished colleagues, I will dwell upon the discussion, the debating points, because the dissertation is quite a good one and the content was already described. I would like to dwell upon the following facts. Discussing the doping effect by 3 valent metals, the author mentions oxygen vacancies needed to compensate the charge. And it seems to me that in doping with 5 valency elements, we could expect the presence of cation vacancies, relevant to the ones that can be found in the spinel in aluminium dioxide, but we are talking about interstitial oxygen. We could talk about interstitial oxygen with cations in the first case, so that is the point that I found a bit strange. Then, talking about symbiote formation of titanium 3 plus and vanadium 4 plus under the radiation exposure, the author demonstrates the reduction of both metals, and the question is what happens with oxygen then, because we could expect that oxygen will be turned into superoxide ions or peroxide ions and so on. but the author is limited by here you use two descriptions at the same time, and can we have this bridge between electron and molecular description? And you widely used abbreviations and short definitions, and it was already corrected in the thesis, as I've managed to see, because sometimes you use several English and Russian abbreviations at once, and as for explanations, you give them a bit later than you give this abbreviation. Then, there are certain remarks that are listed in my review, therefore I won't dwell upon them in detail, but I would like to mention that overall you use a kind of jargonism. You talk about kinetics when you talk about some kinetic dependencies, because according to the definition, kinetics is a section of physical chemistry, but not anything else. So that's a kind of jargonism. And there are such unimportant comments like that. And overall, I would like to mention that these remarks do not compromise the basic content and the credibility of the results that is supported by the literature data, literature sources, and the results can be used, can be widely applied, and they can be used in interpretation of the results of further studies. And I would also like to draw your attention to the fact that the results of this thesis are published in just two works, in just two journals, but rather good ones, and it demonstrates the high level of erudition of our author, and also the thesis on this topic corresponds with the requirements established by the order on the procedure of granting academic degrees at St. Petersburg State University, and I believe that the candidate for the degree, Petr Murzin, deserves the academic degree of the candidate of sciences in physics and mathematics in specialization 010407, condensed metaphysics. And Article 11 of the above-mentioned order is not violated. That's it. Thank you. Thank you. Thank you very much. So, please, Petr, you have the floor. So, the compensation of by cation vacancies is possible, yet as for the materials that we studied, this compensation is not a characteristic one, and I managed to find a fresh article, a newly published article, where they create titanium dioxide with a lot of cation vacancies, and they managed to do that only thanks to the stabilization of a special phase of CO2b, and they are represented by nano threads. And such materials have different characteristics from the ones that we are working with. So the short answer is yes, it's possible, but it's not typical for us. Thank you. Thank you. These are all the answers. Yes, Alexei, are you satisfied? Yes, and as for oxygen, could you please explain? As for the growth of signal of titanium 3+ and vanadium 4+, indeed, in photoreduction of metals, these holes should be localized on oxygen. And yes, we do not state that there's only O0. We can have different forms of oxygen here. And this is connected with this question on vacuum studies. Indeed, in vacuum, we could detect what happens with oxygen. Yet, in this work, we demonstrated that there is a variation between the change of work function and photoactivity. Therefore, this would add certainly to our basic results. Yes, thank you. Now I give the floor to Professor Vadyankina. Olga Vladimirovna, please, you have the floor. Thank you very much. Do you hear me? Yes, I beg your pardon, because I have more questions, therefore it will take a bit longer. Certainly this work creates a very good impression because it's quite an in-depth analysis, and here is a list of my comments that I had. On page 47 of the dissertation, in the table 1, the author gives the results of the changes in phase content for aluminium doped titanium dioxide samples that are connected with the increase of the anatase content up until 18.2%. Maybe that is connected with the distribution of aluminium cations in the structure of a double phase sample, and we should expect the segregation of aluminium cations on the surface of the anatase particles, and this prevents its phase transition to rutile. So the distribution of aluminium should correlate with the distribution of anatase particles in the samples, and if not, how will you explain this expansion of the anatase phase in aluminium doped titanium dioxide up until 18%? Second remark. How representative is this shift of maximum of the peak of titanium 2p3/2 from the concentration of vanadium? So that's a figure 32, and you don't have this dot for non-doped titanium dioxide. So third, explain the choice of the proportions of doped elements for the preparation of the samples of scandium vanadium doped titanium dioxide. Next remark. To all the X-ray photoelectron spectroscopy results, did you have quantitative assessment as regards to titanium? Because when you compare the chemical content in powders with micron dispersity, it would allow to assess the spread of dopants on the surface in this volume of synthesized samples. This information is rather important, and I won't read why. Next, on figure 55, you have the change of the constants of generation of coloring of the centers depending on the concentration of scandium. And we really see this dependence of relative growth of the constant of the time generation for the band 2.69 electron volt. So how do you explain the fact that this maximum speed of generation of coloration centers is as you give it, and it is observed for non-doped samples and with samples with minimum addition of dopant, and for band 2.68 it is observed for sample with a content of 0.75% of scandium. So how can this fact be connected with the maximum photoactivity of the sample with 0.05% of dopant mass? So that is the question on the nature of these bands. 6. What source was used to carry out experiments on studying the colored centers? You don't give the source. Maybe you had filters there. 7. In interpretation of the spectra, you on figure 22, you wrote an idea that this second form of oxygen is relevant to the oxygen vacancies on the structure of titanium dioxide. It can be connected with the presence of adsorbed forms of oxygen on the surface or OH groups. And later you said that it is the relevant to the oxygen in titanium 2O3. So so how can you explain this result? Then 8. How did you calculate the derivative of the area of photoinduced coloring from the concentration of dopant on figure 65? And I believe this position of maximum should be shifted to the left. Comment number 9 on page 19. Using the samples of niobium-doped titanium dioxide, you make a conclusion that according to the results of the investigation on the kinetic coloring and thermo-induced bleaching characteristics, they demonstrate in the structure of the coloring centers of the niobium concentration, that is 0.74. And as for the general comments, that's quite a good work. I don't have comments on punctuation marks because sometimes you lack them, but unfortunately you have this table 6 that could not be read. And my conclusion, regardless of the fact that I have a number of comments, they are mostly related to they can be explained by my interest to this work because I was quite pleased to read it. So they do not; these remarks do not compromise the overall high grade of the work. And this work by Mr. Murzin corresponds meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University. And the author of the work deserves the academic degree of the candidate of sciences in physics and mathematics and specialization 010407 condensed matter physics. That's it. Thank you. Thank you very much, Olga. Now I give the floor to Petr. So, Petr, please. As for the first question, indeed, this shift is close to the era of measurement that was defined as and it was close to the era of the instrument. And if this result did not correlate with anything else, it would be less trustworthy. But on this concentration, we see the peculiarities of other methods. Therefore, it deserves attention. And as for lack of the point on the doped sample, I have it here on this slide. And in this work, we do not compare doped and non-doped samples. We have a comparison of trends that happen in the increase of dopant concentration. Therefore, non-doped samples are the general reference point here, and it's given over here. As for the comparison of results of the measurement of concentration with the methods, such studies were carried out using niobium CO2. We see that the concentration is within the error limit, so they coincide. And if at some point we do not take this error into account and we believe in this increase of concentration registered by the X-ray photoelectron spectroscopy method, we still see this picture, and this increase of concentration on the surface does not explain photoactivity. And as for non-regular oxygen, so we're talking about this figure over here in the upper part, and indeed, for optimal concentration of scandium, we observe more non-regular oxygen. Indeed, as it's mentioned in the question, it can relate to different forms. The key point is that it's not regular. And this prevalence of this form, this local maximum and concentration here, corresponds to the rise in photoactivity and the change of the defect structure that we register by optic methods and APR methods. And as for lack of response in titanium signal, I would like to mention that here in the bottom you see the picture from an article in which titanium dioxide was treated with plasma, and you see that oxygen peak has this elbow, has this shoulder, and this titanium peak does not demonstrate exact peculiarities. They are a bit expanded, but at the same time the signal is quite weak, and maybe it is connected with the fact that that is not such an intensive signal. Therefore, I have this spectrum decomposition over here for this sample. And you see this 4 Gauss functions, and decomposition was quite successful. Why don't we see the titanium spectra? Because the signal is quite weak. As for the position of the derivative, if the derivative is considered along the whole range, the maximum should be moved to the left indeed. But the derivative was considered in the average range of concentrations, where the forms of the absorption spectra do not significantly change, because here on the margins, when the concentration is too small or too large, we see the significant deviation of the form of the spectrum from its general form with mid concentrations. And as for the bands in photo-induced coloring, so that's an object of a particular research. And on our department we do have such studies that are carried out, and there are specific works written on them. But we've managed to find the key point that the centers in which we can decompose the signal for absorption for all series they correspond with the bands that are present in non-doped titanium dioxide, and this demonstrated the important role of these intrinsic defects of titanium dioxide. And the first question on the concentration on the rise of the anatase phase. Indeed, we observe this slowing down of the shift from anatase to rutile phase, and literature sources give us this data as well. Indeed, maybe we can have this situation described in the question when all the heteroparticles are on the surface, are found on the surface. But based on the data that we have, we can see not just separate agglomerations of particles with heterophase, but one single particles in which the atom of dopant introduces local irritation. Therefore, we see the rise of the anatase phase. And the increase of this phase happens in a linear manner with the rise of concentration, and photoactivity of the work function demonstrate maximum. Thank you very much, Petr. Olga, are you satisfied with the answers? Yes, overall, yes. Thank you very much for the detailed answers. Yes, thank you very much for the questions as well. Now I would like to give the floor to Professor Kamanina, Natalia Kamanina. So please, Natalia, you have the floor. Thank you very much, distinguished Chairman, for giving the floor. And I would like to mention once again that according to the rules, my review has all the necessary paragraph on the qualification work. Therefore, I would like to dwell upon the comments that I had as my colleagues. So overall, I liked the work because titanium dioxide, is studied by a lot of groups, and finding your own way here is quite a complicated task. So the questions that I had, the first question, due to the fact that in titanium dioxide doping with different components you change its elemental grid, what impact does it have on the refraction parameters? what is the change of refraction index here? Second question. Did you carry out the measurements of the transmission and absorption spectra of your materials that would give an opportunity to make a forecast on the expansion of the spectral range of the functioning of new composites based on titanium dioxide? Next question. As a test catalytic reaction, you studied the process of phenol decomposition. Are these universal optimal concentrations of dopants for the activity of titanium dioxide in other photocatalytic processes? And next question is connected with the fact that frequently candidates for the degrees use Greek symbols, but they do not use tilted symbols, and the same is true for Greek symbols. But that's, just a short remark, just a recommendation for future work. But I'd like to mention that the work is written quite well, and it was very comfortable to read. And as for the list of works that you mentioned, you have this work on quartile Q1, and it's rather hard to publish such works for Russian authors. And regardless of the comments that I mentioned, I believe that as for the character and as for the scope of studies, as for the relevance of the goals, we all see the practical importance of this dissertation work. And the thesis by Petr Murzin, titled "The Effect of Heterovalent Cation Dumping on the Activity of Titanium Dioxide in Molecular Photoprocesses and Heterogeneous Systems," certainly fully meets the requirements of the order as of September the 1st, 2016, on the procedure of granting academic degrees at St. Petersburg State University. And I believe that Mr. Murzin deserves the academic degree of the candidate of Sciences and Physics and Mathematics in specialization 010407, Condensed Metaphysics. Thank you. That's it, what I wanted to mention. Thank you very much. Thank you very much, Natalia. Now I give the floor to Petr for answers. Petr, please. As for the change in refractive parameters, indeed, we can expect such changes. We did not carry out direct measurements. We worked with powder-like samples, and we cannot directly measure the spectrum of of transmission and absorption, but we can presume that the changes of refractivity may happen, but they are not quite significant. That's what we believe, and this takes us to the second question on the forecast of expansion of the spectral range. On the one hand, we did not measure this transmission and absorption spectrum because we worked with powder-like samples, but we can make such forecasts using the spectroscopy of diffuse refraction. For example, in series vanadium-doped CO2, we've seen intensive absorption, and according to literature data and according to the results of my work, we see that that's not a sufficient condition to study the spectral range. And as for the question on the test reaction, overall, in studying the activity of other reactions, it's possible to expect the change in the position of optimal concentrations, especially if we talk about the mechanisms connected with the transfer of electrons. Yet, in this work, it was established that the rise of photoactivity is connected with the speed of recombination, and it's not a characteristic of reaction, but a characteristic of a material, and this allows us to expect that this part of photoactivity will not change. Thank you. Thank you very much for the responses. Natalia, are you satisfied? Yes, thank you very much. Thank you very much. Very good answers, very good work. Now I would like to give the floor to a Doctor of Chemical Sciences, Ekaterina Kozlova. So, Ekaterina, please. Dear colleagues, hello. As other members of the board, I liked Petr's work a lot, and we know that there is an acute issue of the development of new water and air purification methods, and photocatalytic method is one of the most promising ones. And sure enough, the works in this direction are of particular importance. And a peculiar characteristic of Petr's work is the systemic research. You've just not carried out doping, but you carried out comprehensive research or about the cations that have an impact on the structure of the formed combinations and on their photocatalytic activity. And also I would like to say that the high level, the top quality level is demonstrated by these two publications in high-ranking journals, and I would like to mention that the work is written in rather good scientific parlance. The punctuation is quite good, and as for certain foreign abbreviations, they were already mentioned, therefore I didn't mention them in my reviews. Unfortunately, yes, we do have such a problem. And my main question was on synthesis. I believe that the experimental part of this work is a bit overloaded by the synthesis methods of titanium dioxide, and it's written so that it suits better for literature review. And also there are certain questions about why rutile. Maybe it would be interesting to compare synthesized samples. But these remarks, they do not compromise the high level of this work, and I believe that the thesis, this thesis prepared by Mr. Murzin, meets the requirements of the Order of St. Petersburg State University on the procedure of granting academic degrees. And I believe that Mr. Murzin deserves the academic degree of the Candidate of Sciences in Physics and Mathematics in Specialization 0100407, Condensed Matter Physics. And Article 11 of the above-mentioned order is not violated. That's it, what I wanted to mention. Thank you very much. Thank you. Thank you, Katerina. Petr, please, you have the floor. Indeed, the choice of synthesis method should be placed into the experimental part in order not to make it too volumetric. The motivation was that the reader getting acquainted with the samples would at once understand why I chose this synthesis method. And indeed, the annotated form or samples, that's an interesting object for research, and we do have plans for further work. And for example, niobium-doped CO2 in annotated phase demonstrates completely different electric characteristics, unlike rutile, and this allows us to expect other optimal concentrations and, I believe, more interesting effects in the annotated phase. So we do have such studies carried out in our lab. Thank you. Thank you for the answers. Ekaterina, did you like the answers? Yes. Thank you very much. Petr? Yes. Thank you for the questions. And now I would like to give the floor to Professor Walk for his review. So, please, Professor Walk, you have the floor.
Hello, colleagues. I hope you can hear me well. Yes, I also like also the discussions before. I also like the work of Petr Murzin very much. I guess it was a very detailed study about these doping effects. Nevertheless, I have still 4 or 5 questions which I like to give to the audience and to Mr. Murzin. The first one is it's also related to slide number 9 of today's presentation. where we showed the coloration of the scandium-doped samples, and what is obvious is that the coloration is not the highest for the most active concentration of scandium. The coloration is increasing with the concentration, but there is always this optimum concentration, and maybe you should comment a bit on that. Then I have the second question on the slide number 15 of today, which is regarding the work functions. You mentioned already that niobium is a bit different from the dependence on work function and photoactivity. And maybe you should comment again why this is going in line for niobium, the work function and the photoactivity, but it's always opposite for the other three ions which you dope in. And the third question will be on the co-doping, because you observed that the co-doping with scandium and vanadium is optimum not in a 50-50 ratio, but in a ratio 75 to 25. And I would have some doubts about that, because you one time replace the titanium 4 by a 3-valent ion, on the other hand by a 5-valent ion. And so I would expect that they should go in line to have a charge neutrality of the whole sample. Maybe you should also comment a bit on that. And my last question is then going on more the synthesis aspects which I just discussed a minute ago. Because all your titanium materials, the rutile materials, have a quite low BET surface area. That's about 10 to 30 square meter per gram. What would you expect if you would try to go to samples which have maybe 100 square meter per gram? Is there the same trend, or is there something else in that? But in general, I also said in my report already I'm very pleased by this PhD thesis. This is really very clearly written, and it's also showing very nice figures on a very high level, and which is really supporting the discussion. And so I'm fully convinced that Mr. Murzin deserves to be granted with the degree of candidate of physical-medical sciences in the specialization 01047, condensed matter of physics. And for the German system, I would judge this presented dissertation with the grade magna cum laude. That's from my side, and maybe now I'm keen to hear the answers on the questions.
Okay. Спасибо большое.
Thank you very much, Professor Wark. Peter, please, you have the floor. Yes, thank you very much, Professor. К сожалению,
I have heard the three other, so I will answer not in order, and would you kindly repeat the first one? So regarding the optimal ratio, when we are talking about co-doping, indeed it is not 50-50, which was usually stated as a passivating co-doping concept in literature. And the case here is that that self-compensating defects of titania are always present when we dope samples, which was shown by optical methods and by EPR spectroscopy for the co-doped samples. This, I guess, the case why the optimal co-doping ratio is not 1:1. Yeah. Regarding your question on niobium-doped titania, indeed, anatase and rutile niobium-doped titania act significantly differently. Specifically, niobium-doped rutile is dielectric, while niobium-doped anatase is has much greater conductance. Well, in this work we observed increase of work function, which implies that the Fermi level position shifts downwards. This shift downwards was associated with stabilization of centers like niobium 5+, oxygen T, titanium 3+. This assignment was made due to quantum mechanical calculations which were presented in scientific literature, and experimental data also done by our colleagues worldwide. These centers are inert in terms of recombination, since they have electron neutrality. And it is not the case, as again was shown by quantum mechanical calculation, for anatase doped titanium. In that case, we have electron density spread over greater amount of adjacent atoms. So, indeed, investigations with anatase phase would be interesting. And this also leads us to your question regarding specific surface area. Our synthesis method, solid-state synthesis, usually provides samples with relatively low specific surface area. But it was chosen due to the fact that we end up with the most stable phase of titanium. So moving to higher values of specific surface value, I guess, would be achieved when we investigate anatase phase. And I think we should not make like solid forecasts regarding whether the optimal concentrations would stay at the same position or not. But still, as I said, answering previous questions, the recombination part of photoactivity is characteristic of the material. So we should expect that this part of the equation, so to say, would not change. Yeah. And would you kindly also repeat your first question?
Okay, yes, I can do that. Thank you very much for the other answers. They are very good for understanding that a bit more. If you see on the slide number 9, which you presented today, there is this inset where you showed the coloration, and the coloration of the sample with 0.05 is somewhere in the middle, but nevertheless it's showing the highest photoactivity. And so the question is, how is it going in line the coloration of a sample and the photoactivity?
Yeah.
Why is that not showing totally the same trend?
I see. Thank you. Well, indeed, that's an interesting one, since we have the maximal coloration for 0.25% of doping, whereas maximum photoactivity for 0.05 atomic percent. But if we consider this derivative of absorption versus dopant concentration, we would have maximum exactly at the optimal concentration in terms of photoactivity. We could attribute some physical sense to this derivative like this. It means that with further increase of dopant concentration, we have the greatest changes, the greatest alteration of defect structure of the material. And this is the case for actually our most active sample. So there is no contradiction here. Thank you.
Okay, thank you very much.
Спасибо.
Thank you. Thank you, Professor Walk. Are you satisfied with the answers?
Yes, I am. I'm good.
Okay.
Я
For our Russian speaking audience, I would like to read the words. I would like to comment on these words of Professor Work, magna cum laude, and it means in the Russian language that it is a really good work. So now it's my turn, and I'll try to be short. I'll read it out. Overall, the dissertation of Mr. Murzin is a finished scientific research. It is a relevant one. It has scientific and practical importance, and the result is a novel one. The advantage of the dissertation is that it's quite logical, quite laconic, and the conclusions are substantiated. The dissertation is written quite well. The text is checked well, and that's really an advantage. And as for the provisions brought for the defense, they are quite substantiated, and the new results do not contradict the physics of condensed matter existing results. And it creates the foundation for the forecasting and creation of new photocatalytic systems with a well-controlled photophysical and improved functional characteristics. And this dissertation is certainly a contribution to the physics of condensed matter area. And along with that, I have a range of questions, and I'm going to read them out. So, first of all, could you please explain the assertion? Thus, in heterovalent doping, we should have an electric redistribution of the defect states in the local field of the dopant. That's page 19. It's hard to understand it without energy diagrams. Therefore, on this page 19, I want to get a comment on these words. Second, what is the coordination of your results with a model of optimal area of concentration of dopants depending on the particle size published by Professor Bannemann in Physical Chemistry Journal? So you know this work. Certainly. Third question, the question on the synthesis. Can this dark acidification with the solution of hydrochloric acid have an impact on the photoactivity of the doped titanium dioxide or not? Fourth, how do you explain the presence of the C1s signal of carbon in X-ray electron spectra for doped titanium dioxide? What is the nature of this carbon? Is it a biographic dopant? I didn't find the comments on this quite intensive signal in your dissertation. 5. It was interesting. What is this this level of amorphy of the samples? Can you assess them using the X-ray structural data? Did you perform that? And 6, just a general comment that seemed relevant to me. These terms, 3-valent and 5-valent doping in Russian, I believe they are not just quite good ones, they're a kind of jargonism in the Russian language. 5-valency admixtures, they sound well in Russian, and 5-valency doping in Russian does not sound that well. But overall, the dissertation of Petr Murzin, titled The Effect of Heterovalent cation doping on the activity of titanium dioxide in molecular photoprocesses in heterogeneous systems, meets the requirements of the order as of September the 1st, 2016, number 6821/1 on the procedure of granting academic degrees at St. Petersburg State University. And Mr. Murzin deserves the academic degree of the candidate of sciences in physics and mathematics in specialization 010407 condensed matter physics. And Article 11 of the above-mentioned order is not violated. So, please, you have the floor for the answers. As for indeed, this signal is something that we observe in all spectra, and this is connected with the presence of carbon in the surrounding atmosphere and its absorption on the surface of the samples, and on the other hand it can be connected with the fact that part of the carbon is something that we can find in the instrument, and finally it can be a biographic dopant, and it can be found in the precursors. But even if it's so, it is present, and it, well, pollutes and biographically dopes in a similar amount, and it does not explain the change in photoactivity behavior. And as for the level of amorphy, indeed, we did not carry out this assessment, but overall, judging by the width of peaks, and by the form of peaks, and by the temperature of 100 degrees, we can presume that there's low amorphy of the received samples. And as for the explanations to the rise or drop of energy in the local field of dopants, I would like to use an example here to explain. If we have an introduced atom of 3 valency admixture impurity, as for the mesh of titanium dioxide, it has a negative charge. Then the energy of electron titanium 3+ center should increase, and the reverse is true for 3 valency admixture. And this explains the level of Fermi in scandium doped sample, and it allows us to say that these centers are shallow traps. And as for the terms, I agree that that's a kind of jargonism in Russian, but here they were used to demonstrate the position of the doping elements in the Mendeleev table, and just to simplify the narration. Thank you. Okay. So we've finished our acquaintance with the reviews. All the reviews are positive, and I am to once again ask you, dear colleagues, so judging by the results of these 6 reviews, do you members of the board have any objections, or maybe comments, or maybe additional questions, or we are overall satisfied by the answers that Petr gave us? Yes, that was done quite well. The answers were quite good. Yes, I support. Yes, I have no remarks as well. Well then, now it's time to give the floor to our guests that are not members of our dissertation board. Therefore, I would like to give the floor to our honorary guest, to Professor Detlef Bannemann. So please, Detlef, you have the floor.
Thank you very much, and thank you, Petr, for very nice thesis work, very good presentation, and I've known you now for so many years, and I know that your presentations are really excellent, and so is the presentation of your thesis. If I may, I have a little question which you didn't discuss too much. When you talk about doping, are we talking about the bulk of the particles, the surface of the particles, or are we talking about both? That is my little question to your work. But as I said, I'm really happy about your work. So if I may ask this question, please.
Спасибо большое, профессор Баннеман.
Thank you very much, Professor Bannemann.
Thank you for the question, Professor Bannemann. So, we suppose that this is bulk doping. Firstly, due to the fact that we have relatively low specific surface area, and we do not observe any concentration, any, so to say, special features at the optimal concentration, for example, in XPS. So it's rather bulk doping.
Спасибо. Спасибо.
Thank you very much. Thank you very much, Professor Banneman, for your kind words and for your question. We have no external reviews from our broadcast. That's what I wanted to mention. And now I would like to give the floor to the scientific advisor of our researchers. So please, Alexei, you have the floor. Tell us about Petr and his work. Thank you very much. Good afternoon, distinguished colleagues, distinguished members of the board, distinguished guests. And my review as a scientific advisor can be formal or informal as you wish. The formal one is submitted as a document. And I would like to mention that Petr has been working in our lab since 2014, for quite a long time. We've been working together. During this period of time, he performed the studies that he described in his thesis, in his dissertation, and quite a lot of other studies were carried out with his participation. And Petr is characterized by the fact that he is very active, both socially and in science, and as part of a team of students and PhD students. In 2017, he took the first place on the startup contest in St. Petersburg State University, and also there was a range of other contests that he worked with business ideas. And he actively works with school children, with junior students, freshmen, sophomores. So that is the formal thought that I wanted to mention. As for informal words, for me, a PhD student, as far as I see it, a PhD student becomes a candidate of science when the work that starts with the setting of goals in order to when it works becomes his work, not just the work defined by the scientific advisor. And when this candidate is capable to perform this work independently, when he is able to develop his goals, when he is able to set the new goals, and when he is able to somehow dispute with scientific advisor, because this becomes his topic, not the topic of the offered by the scientific advisor. And in this field, this is a completely Petr's work. It was performed independently at a high scientific level, and it's written quite well as well. And I believe the presentation was also given at the high level. So my opinion as a scientific advisor is that this work fully deserves the academic degree of the candidate of sciences in physics and mathematics in specialization 01, 04, 07, condensed metaphysics. That is my conclusion. Thank you so much, Alexei. So we've approached the final steps of our session, and I am to discuss with you, should we have this closed discussion of the results that we've listened to today, or there is no need for that because we didn't get any negative opinions on the dissertation. Therefore, it seems to me that we can skip this point of agenda. Therefore, in our open discussion, I believe we can give our opinions. But according to my agenda, I should ask, should we have this closed 5-minute discussion of the results just for the members of the board or not? Natalia? No need for that. because everything was quite well presented, all the points and all the answers, and the opinion of the scientific advisor just supports this high level of the academic work. Therefore, I believe there is no need to spend time on that. Olga, yes, I support. My colleague Ekaterina, yes, I support my colleagues as well. Professor Wark.
There's no need to have an...
Okay, thank you.
Okay, thank you, everyone. So, no external reviews. Okay. So, we start the voting procedure. So we start the voting procedure. So the form of this balloting is quite simple. Every member of the dissertation board should say if he or she supports the conferring of academic degree or not. So, therefore, I raise this question on conferring or non-conferring the academic degree to Petr in scientific specialization condensed metaphysics. So we're going to have open balloting, and I would like to remind you that the decision of the dissertation board is valid, is positive, provided more than 50% of the board members, but no fewer than 3 people voted in favor. So we have a quorum, the full quorum. Therefore, let's vote. Let us vote. Alexei, your opinion? Alexei, microphone. Your microphone. Well, so do you support or not? Yes, certainly I do. I support granting the academic degree. Olga, what about you? Yes, thank you very much. I do support this as well. Natalia, what about you? Yes, thank you. I vote for the conferring of the academic degree. Ekaterina, I vote for as well. And Professor Wark?
Yes, of course, I also support.
Okay, спасибо.
So I also vote for the conferring of the academic degree, and thus, by simple calculations, well, the procedure requires to calculate the votes. So 6 voted for, no one voted against, and no one abstained from the vote. Therefore, based upon the results of our balloting, we make a decision on conferring the academic degree of the candidate of sciences in physics and mathematics to Petr Murzin in specialization 010407 condensed metaphysics. That's finally it. We are all working remotely, but we jointly made this decision. I would like to thank all the participants so much. I would like to thank our remote members of the board, to Professor Wark. I would like to thank Professor Barneman for taking part in the session. And I beg your pardon, I missed one point. This important question that I missed. Does anyone have any comments on the procedure? Does anyone have any remarks on the procedure, on our remote procedure? Please voice if you do. And if you remain silent, I judge that you agree with the procedure. I have no objections. That's just a legal point. No, I don't have a remark. But you should have given the word to our candidate. No, I'm going to provide the floor to him, don't worry. No, we're just drawing the conclusions about the organizational points. No organizational remarks? Okay, now I give the floor for finalizing remarks to Petr. So, Petr, please. First of all, I would like to thank the members of the board for taking part in the session, for getting acquainted with my thesis, for the valuable remarks that you've given. And I would also like to add that as for remarks, the misprints and different shortcomings, unfortunately, I can't correct them in the version that was already downloaded to the website, but I printed the new version without these misprints that I had. Certainly, I did not introduce any amendments in the essence of the dissertation, but as for punctuation marks and so on, I corrected them in the newly published version. So thank you very much once again for reading the dissertation, for the valuable questions that really take me forward and make me understand what can be done else. Thank you very much for that. And once again, I would like to thank everyone who supported me in this lengthy way, from the very beginning when I came to the Faculty of Physics of the university, and certainly the entire department had a huge impact, and I would like to thank all the members of the department. I would like to thank my scientific advisor, Professor Yemelin, and thank you very much for this pleasure to see a real scientist at work. And the same is true for everyone that I worked with. So thank you, everyone. Thank you, Petr, for these kind words. And here we declare our session closed. I kindly ask you to turn off the broadcast, but after the broadcast is turned off, we can have a short discussion. And after it's turned off, I would like to say a few words. So turn off the broadcasting. Yes, let's give a hand to our candidate. So, Petr, we congratulate you. And we really hope that that you'll be satisfied with the trust that we've given you, and I hope that we'll see you in further development of your topic. And I would like to address the members of the dissertation board. I would like to thank you for taking part in the work of our dissertation board, and I'm really pleased to get acquainted with each of you, even remotely, because the conditions do not allow us to meet each other in person, yet anyway, the technical capability is something that we luckily have. You also get acquainted with each other, yes, and we got acquainted with two wonderful ladies from Siberia, and I'm very pleased to get acquainted with them, and I really hope that we're going to see each other later on. Alexei, yes? Turn on your microphone. Yes, certainly we'll see each other face to face next year. I hope that next year we're going to see each other, yes. Yes, if the pandemic will be less serious, if this situation will improve, certainly we'll meet each other. And I would like to thank our foreign colleagues for participation. Professor Ward, Professor Banneman, we're greatly thankful to you. And these contacts with Germany for us, they are quite precious in the scientific regard for us, because during this pandemic times, direct contacts were really fruitful, and they supported us a lot. And the previous times when we had a chance to train our students together, and I would like to thank you for that as well. And I hope this situation will improve, and we will continue that in the future as well. So, distinguished colleagues, here I stop our informal part. If anyone wants to talk